We already talked about the effect of substrate in SN1 and SN2 reactions. We know that methyl and primary alkyl halides are reacting faster in SN2, so they are the preferred substrate for SN2 reactions. And we know SN1 reaction prefers the more substituted alkyl halides such as tertiary alkyl halide. So when we have secondary alkyl halide, we see that SN1 and SN2 can occur. But which one is happening? There are a few factors that can help us to make decision that which one is happening on secondary alkyl halide. The first one is the leaving group. So the leaving group, we already talked about it. The best leaving group is a highly stabilized one, and it's usually the conjugate base of a strong acid. So if you look at this chart, iodine is the best leaving group in this chart. So we know in the periodic table from top to the bottom, atoms gets larger. Therefore, the negative charge will be more stable on a larger atom. So iodine would be the number one. Then we have bromine, chlorine. Fluorine cannot act as a good leaving group because it's too small and it cannot stabilize the negative charge. Then we have another group which we call that tosylate. So tosylate is a decent leaving group because that negative charge can be stabilized by resonance over this molecule. So it's very good leaving group. And after tosylate we have water. Now unlike water, OH group is not a good leaving group. So in SN1 and SN2 reaction we can use alcohol, such as this example, as a substrate. However, OH is not a good leaving group, meaning that if you draw such an arrow, it is completely incorrect. So up to here, everything is similar for SN1 and SN2 reaction. Now, there are a couple of ways that we can convert OH to the good leaving group, and these ways are different for SN1 and SN2 reaction. Now for SN1 mechanism, you can use acidic condition to convert OH to the better leaving group, such as HCl, HBr, or hydronium ion. They are all acids. Now look at this example. So under acidic condition, the alcohol can act as a good substrate for SN1 reaction and form the alkyl halide and water. Now let's think about the mechanism here. So when we have these two substrates, something that can happen between them is an acid and base reaction, because HCl is a strong acid. It has lower pKa than alcohol. So alcohol would act as a base and HCl will be our acid. So chlorine leaves. To form this product. Now here we converted the alcohol to the good leaving group, which is water. It's a SN1 mechanism, so water leaves to form the carbocation. Now this carbocation is a tertiary carbocation. Now can this carbocation do a rearrangement to become more stable? The answer is no, because the only carbons you can move the positive charge to are the terminal carbons, which make the primary carbocation. So after this, the nucleophile should attack the carbocation, and so in the previous step water leaves, don't forget that. Now the nucleophile here is the chlorine, so chlorine will attack the carbocation to form this product. Now, do I need to show stereochemistry in this product? No, because the alpha carbon is not a chirality center, so there is no need to show stereochemistry here, and we are only making one single product. Now for SN2 mechanism, we are using tosyl chloride and pyridine, sometimes shown as PY, to convert the alcohol to the good leaving group. So we cannot use acidic condition in SN2 mechanism. So what's happening here? If you imagine we have this alcohol, we can use tosyl chloride. This is the structure of tosyl chloride. And we can use pyridine. So pyridine is like a benzene ring, but one of the carbons is replaced with nitrogen. So pyridine can act as the solvent and as a base. So pyridine will take the proton from the alcohol, then alcohol would attack the tosyl chloride to form this product. So you don't need to know the mechanism for this reaction. Okay, so we are going to form this structure. Now if you remember, we already talked about it. This molecule is the tosylate leaving group. So therefore, if we add a good nucleophile such as methoxide, methoxide will attack the alpha carbon and leaving group leaves to form this product. So in summary, when we have SN1 mechanism and we want to convert alcohol to the good leaving group, we are going to use acidic condition. And in SN2 mechanism, to convert the alcohol to the good leaving group, we are going to use tosyl chloride and pyridine. And sometimes you may see tosyl chloride be written as TSCl. So it's the same thing. Another factor that we can talk about is nucleophile. So nucleophile is the species that donates the lone pair of electrons in SN1 and SN2 reaction. Now if you remember the rate law for SN2 reaction, the rate is dependent on the concentration of substrate and the nucleophile. So it is dependent on its concentration and its strength. Therefore, a strong nucleophile will speed up the rate of SN2 reaction. And the stronger the nucleophile, the faster the SN2 reaction will be. Now, what's considered a strong nucleophile and what's considered a weak nucleophile? So here is the table. Generally, if you compare these two parts, a weak nucleophile is a molecule that is usually neutral, and strong nucleophiles usually are charged. So charge is a very important factor here. A weak nucleophile can be as water or alcohol such as methanol or ethanol. Now, if you convert water and alcohols to their conjugate base, so for example, water water conjugate base would be hydroxide, and for example, alcohol conjugate base would be alkoxide. And as you can see in this table, hydroxide and alkoxide, they are considered as a strong nucleophile. So basically, the conjugate base of any species is a stronger nucleophile. Now, for SN1 reaction, if you remember the rate law for SN1 reaction, it was dependent on the concentration of substrate only. Therefore, it doesn't matter whether you use a strong nucleophile or the weak nucleophile, it cannot do anything to the rate. So it doesn't help with the reaction. And majority of the time we are using weak nucleophile with SN1 reaction because they are cheaper, they are more accessible, so there is no point of using a strong nucleophile when it cannot help with the speed of the reaction. So most of the time for SN1 we are using weak nucleophile, and for SN2 reaction we are using strong nucleophile. Another important factor that we can look at is solvent. Solvent is very important. A solvent should dissolve the substrate without interfering with the reaction. Now for SN2 reaction, we are using polar aprotic solvent. So what is polar aprotic solvent? A solvent that cannot make hydrogen bonding. Meaning that it shouldn't have hydrogen connected to an electronegative atom such as fluorine, nitrogen, and oxygen. So in this table we have a list of polar aprotic solvents. You need to know these solvents. One of the most important one is DMSO, dimethyl sulfoxide. The other one is DMF. You can also use acetonitrile. Sometimes you see that as ACN. We can also use acetone as polar aprotic solvent. So as you can see in all of them, we don't have any hydrogens connected to any electronegative atom. So these are the solvents that we need to use for SN2 reaction. Now, why can't we use a polar protic solvent, a solvent that can make hydrogen bonding? Because imagine if we have bromine as a nucleophile, if we use a polar protic solvent such as water, water can make hydrogen bonding with the nucleophile, which reduces the strength of nucleophile, and SN2 reaction cannot happen. So this is not something favored, therefore we are not using polar protic solvent. However, in SN1 reaction, we need to use polar protic solvent. And polar protic solvent is a solvent that has hydrogen attached to an electronegative atom. Examples of that can be water, can be ethanol, methanol, ammonia. All of them are good protic solvents for SN1 reaction. Now, why do we use protic solvents for SN1 reaction? So during the SN1 reaction, if you remember, the leaving group should leave to form the carbocation first. Now, having a protic solvent is very important because protic solvent can make hydrogen bonding with the leaving group and stabilizes the leaving group. Therefore, leaving group won't reattach to the carbocation to get back to the substrate, because we need to push the reaction go forward. So it is very important to use protic solvent to stabilize the leaving group. Now let's put everything together and compare SN1 and SN2 reaction. So SN2 reaction is a bimolecular process. It's a second order reaction, and the rate is dependent on the concentration of substrate and the nucleophile. However, SN1 reaction is unimolecular. It's a first order reaction, and the rate is only dependent on the concentration of substrate. So about the mechanism, SN2 reaction has a concerted mechanism, meaning that the nucleophile attacks the alpha carbon and leaving group leaves, all happening in one step. So it's a one-step process. However, the mechanism in SN1 is stepwise. So it occurs in multiple steps. Now, about substrate. So the substrate in SN2, we prefers the less substituted alkyl halide. So we prefer methyl over primary over secondary, and with tertiary it is basically unreactive. However, for SN1 reaction, we have the opposite order. So it is fastest with tertiary, then secondary, primary, and methyl at the end. So basically methyl is unreactive in SN1 mechanism. Now regarding the stereochemistry, so in SN2 mechanism we have inversion of configuration. So we have inversion of stereochemistry. In SN1 reaction, we have both inversion and retention, so mix of stereochemistry. So we have both inversion and retention. So we are forming racemic mixture. Now about the nucleophile, so SN2 requires strong nucleophile such as hydroxide, methoxide, for example iodine, all the halogens. And SN1 reaction, it requires weak nucleophile such as water, methanol, ethanol. Now the solvent for SN2 reaction should be polar aprotic solvent such as DMSO, DMF, acetone, and etc. And for SN1 reaction, the solvent should be polar protic solvent, such as water, methanol, ethanol, ammonia. Now let's look at these reactions and decide what substrate or reagents or products you need for each of them. These are the type of questions that you should expect to see in the exam. So let's look at the first example. In the first example, we have an alcohol. It's a secondary alcohol. Now, since it is secondary, it can either do SN1 or SN2 reaction. Then we need to look at the reagent that we are using, which is HBr. So HBr is an acid, and if you remember, we had a way to convert an alcohol to the good living group under acidic condition, and this is just happening when we have SN1 mechanism. So to draw the product, let's see what's happening here. This is the substrate that we have. So the substrate will react with HBr bromine leaves, okay, to form this product. Now water is a good living group, so water leaves the molecule to form a carbocation. Now, can this carbocation do rearrangement to become more stable? Yes. It can do H shift to form this stable, the more stable actually, carbocation. Then in the next step, bromine will attack the carbocation as a nucleophile to form this product. Now, do I need to show stereochemistry here? No, because this carbon is not a chiral carbon. These two groups are exact similar. Therefore, we only make one product, which is this. In the second reaction, the substrate that we have is also secondary, so it can do SN1 or SN2 mechanism. Now we need to compare the substrate and the product, so we clearly see inversion of stereochemistry and no retention product formed, meaning that the reaction is happening through SN2 mechanism. Now, if you look at the substrate is an alcohol. We know that OH is not a good living group, and we know a way to convert OH to the good living group in SN2 mechanism, which is use of tosyl chloride and pyridine. So in the first step, we are going to use tosyl chloride and pyridine to convert this OH to the good living group. And then in the next step, since it is a SN2 mechanism, we need to use a strong nucleophile. And we replace OH with SH, so we can use SH as a good nucleophile. And most of the time, the nucleophile is accompanied by a counter ion, so we can use sodium hydrosulfate as a good nucleophile for this reaction. So remember, you cannot do these two steps together. They should be separate. Otherwise, there should be a competition between making the OH a good living group and this nucleophile attacking the tosyl chloride. So we need to do that separately. In the third reaction, so we can see water. Water is a solvent that is used, so it is a good sign for SN1 mechanism because water is a protic solvent. Also, if you look at the products, we have a mixture of enantiomers, so we formed racemic mixture, and both of them are good sign for SN1 mechanism. Now to draw the substrate, so we know that this is our alpha carbon, therefore I will draw the same structure. Okay, now to the alpha carbon I need to attach a good leaving group, and that good leaving group can be halogen. So it doesn't matter whether you put the chlorine in wedge or dash, because this mechanism is happening through SN1, and in SN1 mechanism we are forming carbocation, so which is completely planar, so it doesn't matter whether it is in wedge or dash, we are going to get the same products.